So it's a great honor to speak at this conference. So thank you for the very kind invitation, and thank you for the very kind introduction. So. Okay, so hopefully you can see. Perfect. So now I've shared the screen. I've completely lost all of Zoom. So if you could just tell me that you can see the screen okay.
Sure, we can see.
Perfect. Excellent. So so I just thought I'd begin by just showing where Liverpool is in the UK, in the United Kingdom. So we're in the northwest of England, up here, and Liverpool is quite a unique city in the United Kingdom, as it actually has two cathedrals, a Protestant cathedral and a Catholic cathedral, and they sit either end of a very long road within the city. And here's just some images of the waterfront and our university square. And as well as two cathedrals, as some of you may know, we also have two football teams, Liverpool and Everton. So as in the introduction, so I'm the director of the Stevenson Institute for Renewable Energy, and we do research on batteries, on ways of utilizing carbon dioxide and also solar energy and thermal energy storage. So I will talk about my work on batteries for today. First of all, I'd like to acknowledge my group whose work I'm going to show here today. So this is our last group photo taken last year. So this is in person form, and also this is also acknowledged to former group members, which have been captured beautifully in Lego form as well. And also to acknowledge my collaborators within the UK and around the world, and also the funding agencies listed below. So, so today I'm going to talk about our primarily our in situ and operando spectroscopy that we've been developing at Liverpool. But I thought I'd just start by just defining what we mean in the difference between, say, in situ and operando. So you have to go back to, so this is a Latin phrase, and it means that we're on site or in position. So we're examining the electrode on the specific site. And sort of in a sort of more recent term of operando, which is been coined by Miguel Benares in 2000, and this is borrowed from another Latin phrase, operando, which means working or operating. So when you read that someone's done operando spectroscopy, it means that the spectroscopy has been done in place and, importantly, under realistic operating conditions. Ideally, what we want to do is to examine the electrode interface with various spectroscopies and understand different processes in the actual commercial cell. So here's just a picture of the jelly roll unrolled for the 18650 lithium-ion battery, and some particular techniques are quite adept at doing, say, completely operando studies, such as tomography, for example. But obviously, with optical spectroscopy, we need to get optical access to the cell. So, in terms of defining whether we've done an in situ experiment or an operando experiment, I like to sort of define it a little bit more specifically to our activity. So whenever we use, say, a sort of glass cells, where the electrolyte to electrode area ratio is high, so we have a significant electrolyte volume, I call this an in situ experiment. And then when we've used a specialized cell, it sort of gives us a sort of coin cell geometry in which we have an optical window access the electrode whilst it's under operating conditions, I define this as an operando experiment. And here the electrolyte to electrode area ratio is coming closer to what you'd get in a practical lithium-ion cell. So optical diagnostics are being increasingly applied in battery studies. And I'd just like to acknowledge Jason Porter from the Colorado School of Mines for loaning me this slide, as it shows very nicely when doing a sort of literature search. So if you look for optical techniques applied to batteries on Web of Science, you can see this very steep growth in the number of articles that have appeared over the last 30 years. So why is this the case? So optical spectroscopy, it provides much needed chemical information on the both on the electrolyte, but also on the electrode and the electrode-electrolyte interface, the interface between the solid and the liquid phase in a liquid cell, and also the solid-solid phase of an all-solid-state battery as well. And gives you much needed chemical information, as you can see here. This is typical Raman spectrum. So we have bands relating to specific functionalities and vibrations, and it can give us information on, say, the coordination of lithium in the electrolyte. We can also look, if we're looking at the electrode, to see additional bands which may indicate different compounds are forming at the electrode surface. We can see how the band shape changes, it becomes more broader, or there could be a band shift, and so we can get some very subtle information about all the different areas of the around the electrode and the electrolyte and the interface. And this has really been enabled. So the developments within the lab and also commercially, there's now quite an array of different companies selling optical cells, which both enable in situ and operando studies. And also, I'd just like to concentrate on why these optical studies are really important in understanding processes happening in the battery. So here we have a reaction pertinent to the lithium air or lithium oxygen battery, where lithium is reacting with oxygen and electrons, and you're forming this lithium peroxide. Now, on the whole, it looks a fairly simple and straightforward reaction. But what I like to remind my undergraduates when I'm teaching them is that in electrochemistry, many things can happen at once, and what seems on the surface a very simple chemical process or electrochemical process, this is not necessarily the case, and we really need to probe much more deeply. Now, if we look at all the processes that can happen on the way of forming the lithium peroxide and also its oxidation back to oxygen, you can see that in reality, it's a much more complex set of processes that are taking place, which really begin when oxygen is first reduced. It can either be absorbed onto the surface or in solution, and so you can form the superoxide either on the surface or solution phase. And you can see all the different equilibrium here taking place, and this all depends on the on the type of solvent and salt concentrations within the electrolyte, which sort of guide these equilibria. And so once on the surface, it can react with a lithium and form the superoxide, lithium superoxide. And again, it can then just disproportionate, and you can form a singlet oxygen, and you can then form these different various forms of molecular peroxide, sort of a very thin layer of peroxide on the surface, or if it's in solution, it can precipitate out and form very large crystallites of the peroxide. So this just highlights why we need these diagnostic tools in really pinning down and understanding these reaction mechanisms, and understand if we do vary certain parts of the solvent with its different donor number or acceptor numbers, how that influences these set of reactions. I'd just like to now highlight some of the sort of historical highlights in optical diagnostics applied to different electrodes, and I've selected these, which are sort of historical highlights, which are sort of pertinent to development of techniques which are sort of interesting to be applied to battery electrodes in particular. And if we go back to the start, where in 1966, Mark and Pons were the first to report an IR technique with an optically transparent electrode, which was used to monitor reactants during an electrolysis reaction. So this is the first sort of in situ optical electrochemical experiment that was reported. And this is then the first transmission infrared cells. You have you have a gold mini grid, and there was looking at sort of the redox chemistry of certain organic materials in this transmission cell. Then in 1973, this is where in situ Raman was first reported, and this was by Fleischmann, and he was looking at the surface of mercury electrodes under potential control. And so this is sort of the birth of in situ Raman, and sort of the very next year, his next paper, where he was looking at a roughened silver electrode. This was then the first reported observation of the surface enhanced Raman effect. Then into the 80s, we have now in situ infrared reflectance that's first demonstrated, and in the following year, using this technique snifters, where importantly there's a Fourier transform to allowed much greater sensitivity whilst doing the infrared measurement. In 1987, researchers began to use spectroscopy, particularly infrared, to look at much more complex electrode interfaces. And so for those working in the battery area, you've come across this term of SEIRAS, the solid electrolyte interface. So this is the layer that forms primarily on negative electrodes, particularly on graphite and lithium, and the intermetallics as well, and it has a sort of a very complex composition. It prevents further electron transfer and further reduction of the electrolyte. This is when Arbach began these studies. Now to go to the sort of more modern era, the new techniques start becoming much more advanced and more focused specifically on battery electrode investigations. So in 93, we had the first demonstration of in situ lithium dendrite imaging with optical spectroscopy, and then in Osawa first demonstrated the surface enhanced infrared absorption spectroscopy, and we'll talk a little bit more about that. I'll show some of our data using this very nice technique. The first Raman, in situ Raman, where there was investigation of the lithium insertion into graphite. The negative electrode in the lithium-ion battery was in 95, and this is the first study in 98 where they used in situ infrared to look at the formation of this solid electrolyte interface. And the Raman technique was further developed in this demonstration of using a confocal Raman cell, so you could then begin to get some spatial resolution on the electrode surface. More say exotic techniques such as some frequency generation, looking at the absorption of propylene carbonate onto a lithium-ion positive electrode, a lithium cobalt oxide, and using a variation of surface enhanced Raman, which I'll discuss in a lot more detail, with the acronym SHINERS, and we'll see what that acronym stands for, was applied to battery electrodes, particularly on silicon, looking at the formation of the solid electrolyte interface on silicon electrodes. And the final sort of example I want to just highlight was in 2015, where near field infrared was demonstrated on lithium-ion electrodes. And what's really nice about that is that we were able to sort of see the granularity of the SEI as the near field allows us to approach a 50 nanometer spectral resolution, so really get very detailed and very local information on the chemical nature of the SEI. So these are some of the important developments I wish to highlight. So within our research group, we carry out both infrared and Raman, advanced Raman spectroscopy. And as I mentioned, we use this technique, which has this very long acronym here of attenuated total reflection, so ATR. So some of you are probably familiar of using ATR window for an infrared, and surface enhanced infrared absorption spectroscopy, which has the part of the SEIRAS. What all this long technique name really is essentially is telling you is sort of how the experiment is done, what is the geometry of this. So we have an infrared beam which comes in through a prism, either silicon or zinc selenide. We've grown a very thin gold layer film on the surface, and this infrared beam can penetrate and probe the sort of within nanometers of the electrode electrolyte interface, that region between. And so we can get very surface specific spectra from the interface as we're under potential control. And I'll talk about that at the end of my talk today. We have our various flavors of Raman spectroscopy, surface enhanced Raman, where we have these bucket cells and we have a rough and gold electrode. And as I'm focusing a laser. You can focus a laser onto the gold electrode and then apply a potential and see what sort of components are forming or being degraded on the electrode surface. And then we also use this technique of shiners, where we can put, other than having our, say, plasmon on a roughened gold electrode, we have it isolated within a gold nanoparticle, and we put a silica shell around our particle. So it's isolated, and so we can put these plasmonic particles onto any electrode surface and get our SEIRAS enhancement in this manner. We do operando Raman spectroscopy microscopy as well, using a sort of coin cell configuration, and we look at both battery and super electrochemical capacitor systems with this technique. And then finally, a technique we've in the last few years been looking at and working with the Central Laser Facility in the United Kingdom is this technique of Kerr-gated Raman, where we have an operando cell, and we can do electrochemistry. But this technique is interesting because the use of this gate can remove any fluorescence background. And so this is an example of an important salt in the lithium-ion battery, the lithium hexafluorophosphate salt here. And so with typical Raman, it has a sort of background fluorescence, and so you can't measure any of the bands. So it's very challenging to measure the bands for this without getting a quite substantial fluorescence background. However, when you have this Kerr gate operational, you can filter out the fluorescence, and then you can capture a very clean Raman spectrum of your compounds. And so we're using this to measure electrodes in various lithium electrolytes to see to gain much clearer information, because usually we'd get very sort of we get spectra of very large backgrounds, but we can now measure with much clearer spectra. So what I'm going to talk about today is our metal oxygen cells. So here we have the lithium-ion cell, where you have your positive electrode of lithium cobalt oxide and negative electrode of graphite, and lithium ions shuttle between the two through intercalation reactions. So the metal air cell works slightly differently. So you have a lithium, in this example, lithium metal electrode, where you strip and plate lithium. And as you strip the lithium ions, you can reduce oxygen on a porous electrode and combine electrons, which are doing useful work, to grow this lithium peroxide within your cell. And then what's been found is that this reaction has some reversibility, and this is part of the challenge of the lithium-air batteries, to try and get this much more reversible and understand how to control some of these side reactions. And so you have an operational cell where you're on your discharge, you're forming the lithium peroxide, and when you're charging it, you're oxidizing back to oxygen. So you have an open cell where oxygen is moving in and out of the electrode. And the motivation for this is just a very simple back of the envelope calculation, which shows that you can get much greater specific energies, theoretical specific energies, when you're doing this type of chemistry rather than the intercalation chemistry. So just to introduce Raman spectroscopy. So this is a spectroscopy that can investigate chemical bonding of electrode species. It's shine a coherent light source, such as a laser, at your sample, and most of the photons are going to be elastically scattered or Rayleigh scattering. A small number, so 1 in 10 to the 7 photons, are inelastically scattered, and so this is the Raman effect, and this scattering, particularly the Stokes, where you lose some of the energy, and this difference in the energy is related to the vibration of the chemical bond. So for bulk samples, the sensitivity of Raman is suitable, but if we want to look at the interface, we want to look at absorbates on the interface, this signal is way too weak. So we need really to enhance this signal in order to detect sort of very small concentrations at the interface. So what we're interested in doing is to use surface enhanced Raman spectroscopy, and this can produce enhancement factors up to 10 to 11. So we have a plasmonic substrate which enhances the Raman signal, and this is usually limited to gold or silver electrodes with a sort of nanoscale roughness, where we can detect these species. But this sort of limit says to say gold or silver or maybe even copper. But when we're looking at battery electrodes, typically these are not the main components or the electrode interfaces of interest. So we want to get an enhancement on an electrode or a carbon surface, or even if we're doing very fundamental studies to look at single crystals. We need an alternative method to study the electrode interfaces. So this technique is that what we use is shell isolated nanoparticles for enhanced Raman spectroscopy. We use these Shiner's particles, which we have a gold core, nanometer core, where we have a silica shell on the surface, and we can put these we can put these particles down on the electrode surface, and we can use them to enhance the Raman signal at the electrode interface, and so it can be used on any electrode substrate, and they can be optically inert, and we can get enhancements of around 10 to the 5 for this. So one of the important things about the shell is that it has to be of a certain thickness. If it's too thin, then you're going to get pinholes. And so what you're going to do is get the information primarily of absorbates on these pinholes on the silica shell. And if you have it too thick, then the distance, then you're not going to get any enhancement at all. And so here we have just a simple graph here, just showing the relationship of our SEIRAS surface enhancement intensity with the distance from the electrode surface. And so there's a sweet spot where we can avoid having pinholes, still have a suitable enhancement, and this is around 2 to 3 nanometer thick of a silica shell that can be put on the surface. And so here we have transmission electron microscopy image of a Shin particle, shell isolated nanoparticle. Then we have our gold core, and this is about 50 nanometer diameter. And we have a sort of a 2 to 3 nanometer uniform silica shell that's been grown onto these particles. And so this just highlights the power of the spectroscopy. So as I said, we can put this on any electrode surface, and so this is an example of putting these particles on a piece of planar gold. And so you can see the sort of coffee rim of putting these particles down. So these are all our nanoparticles on the gold surface, and then we add pyridine onto the gold, and the pyridine absorbs onto the gold surface. But with conventional Raman, there's the particular band for the absorption of pyridine, you can't detect it. It's too weak. So only where we have, as you can see, this is the Raman map of these particles on the surface. So dark is there's no enhancement, and the red we have very strong signal from the pyridine. So we can observe the absorbed pyridine on the gold, and that matches very well to where the location of these particles are. I'm going to show now an example that we've used these shyness particles on, and this is to investigate the formation of superoxide. So if you remember back where I showed all the reactions happening to form in a lithium air battery. So this is the first step of adding an electron to oxygen, and here we have our cyclophotomegram where we're sweeping the potential to lower potentials, and we get to a point where the electron is transferred and oxygen is reacting to form the superoxide. And as we sweep back, we can see the reverse reaction where we're oxidizing the superoxide back to oxygen and the electron. And so we can compare our SEIRAS surface and our shyness result. And so with the SEIRAS, we can reduce the potential, and we can see the band, a Raman band, which is related to the oxygen-oxygen stretch of superoxide, and at the same time we have the absorbed superoxide species from this gold oxygen stretch as well, which is appearing. And then when we repeat this with our shyness particles, we see again the same these same bands appearing, demonstrating. So this was our first work on this, that shyness is a practical alternative to surface enhanced Raman in these systems which are pertinent to lithium oxygen systems. So this just highlights some of the recent sort of work we've been doing within the field of metal oxygen batteries. So we've been using single crystals to really unpick and understand some of these reactions taking place within the oxygen reduction, oxygen evolution reaction in the presence of lithium. We've used very well-defined electrodes, so single crystals, to compare different reactions of sodium and oxygen on different surfaces, and we've observed using shyness of different reaction pathways where some Pacific surfaces, we just see a sodium superoxide species. Some surfaces also allow the formation or promote the formation of a molecular sodium peroxide on the surface. And so we've identified this surface effect on driving different reaction mechanisms. And I'm going to talk about two recent pieces of work from our group, where instead of lithium, we've been looking at how calcium. So calcium is divalent, so calcium 2+. How that influences the the oxygen reduction and evolution reaction in non-aqueous solvents. And we've been using spectroscopy and to sort of guide us in designing electrolyte design for metal air batteries, specifically on lithium air batteries. And so I'll talk about both, and this is just to highlight that what we found when we add calcium, we generate an interlayer which traps the oxygen and counter superoxide on our tetrabutyl ammonium. It's trapped at the surface, and so when it's reoxidized, we get a very distinctive peak, and so we can get a sort of trapped interfacial redox at this interface. I'll start by just giving some highlights on our electrolyte design. Here we've so the motivation of the work was to develop an electrolyte for a lithium oxygen battery which was stable to both the lithium metal and also lithium metal in the presence of oxygen, but also stable for the positive electrode as well. And so we started off by looking at a symmetric cell of lithium. And so we took a salt and a solvent, so methyl sulfoxide and lithium trifluorosulfonyl imide here. And if you put this in and you cycle, the lithium will slowly react with the methyl sulfoxide, and so get very uneven stripping and plating, and you consume all your lithium. So this is so this solvent is very unstable against the lithium metal interface if it's not properly coordinated. And so what others have reported, that if you add an ionic liquid into this mixture here, you get much more stable cycling, but as you see, there's a gradual increase in the overpotential stripping and plating the lithium. But if you optimize the solvent, ionic liquid and lithium salt, so we have a ternary mixture in this electrolyte, we can get much more stable lithium stripping and cycling. So we now have our optimized blend of these different components, and as you see, we get very even stripping and plating, low overpotentials, and over 900 hours of stripping and plating still running. And we've shown it's also stable in the presence of oxygen. We can get this same behavior, and because we've got an ionic liquid, we've developed a solvent mixture which has much lower volatility. So this is very important in a, say, air battery or open battery, because you don't want your electrolyte to evaporate and your cell to dry out. So now we have our optimized electrolyte for the lithium side, and so what we did then was to test this against a porous carbon in a full lithium oxygen cell. And so we selected a non-optimized electrolyte blend. So just to add first, so this is sort of this is all the different compositions we investigated, and we use spectroscopy to understand where the critical ratio is, where all the methyl sulfoxide is lithium coordinated, and this stabilizes our dimethyl sulfoxide. And so we looked at two blends, a non-optimized and an optimized blend within this region here. And so within our cells, we cycled this, and so from our optimized, where we're using this on the surface, a very unstable solvent, it can be stabilized by carefully coordinating, having careful lithium coordination within this. We can get much more stable cycling for over 50 cycles, and it still has some cyclable capacity of about 100. We see that when we have a non-optimized ternary blend, the cycling decays and the cell is dead by 60 cycles. So we've optimized electrolyte to brode stable along the cycle life. And so what we're working on now is to investigate different types of our porous air cathode material to try and optimize this system even further. So if we look at this phenomenon of trapped interfacial redox, so what we found when we added calcium to our non-aqueous electrolyte was that it formed this calcium oxygen interlayer, and it provided an ability to trap tetrabutyl ammonium at the interface, and this meant that it was much more readily available as it's at the interface, as it's trapped, to be oxidized again. And so we observed this phenomenon. We use spectroscopy to characterize what is happening. So typically when you have this composition of tetrabutyl ammonium, so you have this ammonium salt with these long butyl chains here, we get quite reversible cyclophotomegrams. Then if we add any calcium, a calcium salt, so we've replaced our tetrabutyl ammonium with calcium, you see that it becomes irreversible. We can't oxidize back any of these components that are formed. However, what we noticed, is very important to notice, is that this does keep cycling. Whatever's forming on the surface when we have calcium is not completely passivating. So the electrode doesn't become passivated, and so we can still have some reaction taking place. So we did wonder that if we combine the calcium and the TBA, whether we'd get any improvement in the reversibility. And if we have similar concentrations, we again see this irreversibility, reversible process that takes place. But if we reduce the calcium concentration by a factor of 10, after a number of cycles, we start to observe the growth of an oxygen evolution peak. And so we were able to then oxidize some of the superoxide that we produce. We thought this was very, very interesting. So we did some rotating disc electrode experiments to see trying to understand, because the superoxide goes into solution, to see where this is ending up. In the initial cycles, what we see, we get this irreversible process, and we can see when we have the rotating disc electrode on at the ring side, we're able to collect and oxidize some of this oxygen superoxide that's produced. So it indicates that our superoxide initially is going into solution. After a number of cycles, we now have this a well-developed calcium oxide interlayer. And so we now get this reversible process. But when we have this reversible process, when we look at our ring electrode, we don't see any positive current. So whatever's forming at the electrode surface is trapped at the interface, remains at the interface, and is not able to then go into the electrolyte to then be oxidized at the ring of the electrode. We then did surface enhanced Raman spectroscopy to understand what are the species that are forming at the electrode surface, and what we see is again the formation of a oxygen for superoxide and a gold oxygen interaction, which indicates that the active species at the interface is this superoxide. And just to note, what we didn't observe was any other type of calcium species, be it calcium superoxide or calcium peroxide. We didn't observe any bands of these compounds forming. whatever this the nature of this amorphous layer is some sort of amorphous calcium oxide layer that's on the surface that has the ability to trap, to not allow the diffusion out of this product of the TBA and the superoxide. And if there are any electrochemistry, you note that this oxidation peak does not have this very nice trillion diffusion path. It looks almost like we're stripping a metal from a surface. So we have a very sort of abrupt and sharp peak for the oxidation. And this also guides us to think about this trapped species in this calcium oxygen interlayer on this in this system. Okay, so I'm going to now finish by highlighting to you some of our work on surface enhanced on our SEIRAS, our surface enhanced infrared absorption spectroscopy. So what we're able to do is to get much more specific information of the electrochemistry that's happening at the electrode surface. And so what we put on a prism here, it's silicon or zinc selenide, we evaporate a very thin gold layer, and it has this sort of nanostructure. On the surface is about 20 nanometers, 16 to 20 nanometers thick, perchlorating network of gold, and so this is our working electrode. And so why do we do this in this configuration? Generally, if you think about doing infrared spectroscopy, we could bring the beam in from here and look at the electrode. We'll have to go through a very thick layer of electrolyte. So essentially all the infrared information we'll get is just the information of the bulk electrolyte. So we bring the beam in from below our cell here. So we can see our cell sitting on our optical device. So our infrared beam is brought up here and then reflected back down. And then, because of our configuration, we're only really probing the first sort of 10 nanometers thick of this layer within the electrode surface. And so we have this cell which is set up specifically for looking at oxygen electrochemistry, which is pertinent to metal layer batteries. And so we have counter and reference electrode, and we're able to then bubble in very dry oxygen in our glove boxes in order to purge the cell before measuring. So most of you are probably very familiar with infrared spectroscopy and know what an infrared spectrum looks like, but I just thought we plot a different spectrum, so I thought I'd just take a moment just to explain so you can interpret these spectra for yourselves. Is that when we do our infrared spectra, we take a reference and then we subtract, and then we subtract this, and so our first spectrum at our open circuit potential should be a flat line. So we haven't done any variations, and then we start to switch potential, and if there's no change at the interface, our subtracted spectra shouldn't change. But at a certain point, when we get to the sort of redox peak, or we start changing the speciation in the double layer at the electrode surface, we'll start to see positive going peaks, which are defined as species lost from the interfacial region, and we'll have negative going peaks, which indicates a new species present at the interface. So when we start to see these types of features, this indicates a change in the speciation at the interface. So if we look at reduction of oxygen reduction evolution reaction in the presence of lithium, so here we have our cyclophotomegram here showing this. So we have lithium triflate in methyl sulfoxide, and so here's our initial spectrum. It's a little bit wavy, but essentially it's flat. So this is our open circuit potential, and as we reduce the potential, we see our redox peak where oxygen has been reduced, and we start to see some negative going peaks. So this means something is appearing, something is growing that wasn't there previously at the interface. if these positions 780 and 1130, these bands can be assigned to molecular lithium superoxide and molecular lithium peroxide, and this is very interesting. So this due to selection rules, if you had the crystal lithium peroxide, this band would be silent. In the molecular form, we do see this band, so we're able to see molecular species at the interface, and we also have evidence of absorbed species, particularly of the lithium superoxide, because there's what's known as a Stark shift. So these bands are very sensitive to the change in potential, and so will shift in position. And so this indicates that our species are certainly within the field and absorb close to the electrode interface. And we repeated this with sodium, so sodium oxygen battery, and so we have our flat spectrum here. And as we switch this potential, we see that we have a negative growing peak, which can be assigned to sodium peroxide, and because we can fully oxidize this system without oxidizing our gold electrode. As we sweep back again, you can see that we again return to this flat part here, showing that we've completely removed our sodium superoxide from the surface. So we've done a lot of work applying our enhanced Raman absorption spectroscopy technique to look at the speciation on metal oxygen battery electrolyte systems, and we've shown that direct proof of the presence of molecular lithium superoxide, lithium peroxide, and sodium superoxide is at the interface, and we've seen that it's a very powerful methodology for detecting solution-based redox species for oxygen electrochemistry at the interface. So just to conclude now, I just want to sum up some just general thoughts. So what's been sort of discussed is that vibrational spectroscopy provides very detailed chemical information. So hopefully I've demonstrated this in the talk of electrode processes at the interface. We can use these powerful spectroscopic techniques to really look at the nature and the number and species of present. We can follow progress of electrochemical reactions, start to unpick and understand reaction mechanisms, and look at degradation pathways. So certainly the commercial availability of commercial cells and greater interest within the academic community of making homemade cells. There's a lot more information of how to make operando experiments much more accessible to the community, and particularly Raman infrared methods, they provide a unique level of interfacial sensitivity, either under in situ operando conditions, which if you have a Raman or infrared instrument, it's a reasonable budget to now purchase a specific cell so that you can get very sensitive measurements within your laboratory. So with that, I'd just like to thank you all for your very kind attention, and be happy to answer any questions.